Welcome back to this course on C programming and assembly language. We are in module 1, and last lecture we abstracted out the model of the memory as follows. We said that a memory is a simple black box. It's a random access memory that has a bidirectional data bus and a unidirectional address bus. So, this is my data, this is my address. So, here I have the microprocessor which is controlling the memory by issuing various commands. So, this is a mu-p, and the memory also has commands called read and write, and these are not being controlled from elsewhere. The microprocessor again issues these commands at appropriate times in order to read or write to the memory. So, in this lecture let us look at the necessary abstraction of the microprocessor that we need for this course. So, let us start with the basic utility of a microprocessor. A microprocessor is meant to execute a program that is stored in a memory. So, the job is to execute a stored in memory. So, let us assume that this program is stored from location x to location y. So, let us assume that there is a location x in the memory where the program starts and a location y where the program ends. The job of the microprocessor is to fetch instruction by instruction from this particular starting location and execute one by one until it reaches memory location y. So, traditionally a microprocessor does the following tasks. It does what is known as fetch, decode and the name fetch suggests what it should do. The idea is to fetch a particular instruction from the memory, then decode it and execute the instruction accordingly. So, if I denote this fetch by F, decode by D and E and execute by E, and let us assume that there are m instructions between location x and location y, then what the microprocessor does is it actually does fetches the first instruction, decodes the first instruction and executes the first instruction. Then it fetches the next instruction, decodes the next instruction and executes the next one, and so on, F3, D3, E3 and all the way to FM, DM, EM. At this point I have to mention that microprocessors have come a long way, where they do not just execute this fetch, decode, execute cycle serially. It does it in what is known as a pipeline manner. So, while the instruction is being fetched and decoded for instruction 1, and then the first instruction is being executed in the microprocessor, the data bus happens to be idle during the execution phase, and therefore you can pre-fetch the next instruction in that period. So, F2, D2 and E2 will happen like this, F3, D3, E3 happens and so on. So, you can clearly see here that in modern microprocessors, because of this concept of pipelining, instructions are prefetched and they end up getting a much better throughput from the particular microprocessor. So, in order to perform this fetch, decode, execute process in a loop, we need to see what all a microprocessor has to have, and that is the exact abstraction that we are going to deal with in this particular lecture. So, F, D and E, in order to perform this, what do we need? So, let us start with fetch. You have to go and fetch a particular instruction from the memory, which means that I need some place in my microprocessor to store an address of where this code exists in memory. So, the first requirement is need code address. And this is precisely satisfied by what is known as the instruction pointer register. So, I have an IP which is and if in 8086 it is 16 bits in length and the register was called IP. As you move forward into the other x86 architectures, 286, 386 and down to the Pentium 4s, this would essentially just be called EIP, where this E stands for extended, and this is true for any other register in the microprocessor as well, as you will see a little later. So, the way we start is we load this location X into the instruction pointer and tell the microprocessor to start executing the instruction from that particular location. So, here you load location underscore X into EIP and you start the execution. So, as the microprocessor fetches a particular instruction at location X and decodes that instruction, the microprocessor will know exactly where the next code or the next instruction is in memory. So, therefore, it can automatically calculate what the next address should be and where the next instruction is located. So, automatically EIP is now incremented plus N. N could just be the next byte or it could be the next word or the next D word. It depends on the instruction size, right? It depends on what is known as the opcode size. So, the microprocessor during the decode phase knows exactly what this number N should be and automatically increments the instruction pointer to the new address and continues this fetch, decode, execute process. So, that is with regard to the code. Now, let us come to the execute part of the instruction. The decode, by the way, is pretty straightforward. It is just a combinational logic where you decode what the instruction should be and invoke those registers and so on. So, there is nothing specifically needed for the decode as far as our abstraction goes. So, let us now look at the execute part. The execution typically is going to refer to some sort of an arithmetic or logical instruction, or it could even be some sort of a data movement from one location to another. So, what do we need in order to implement this execute part in a microprocessor? So, typically if I take my ALU which is something like this, my ALU, you have two operands, right, operand 1 and operand 2, and typically these, at least one of this will end up being a general purpose register. So, you have a general purpose register here, okay, and the other operand could be something more generic. We will come to what those operands could be, right. So, in order to perform any ALU operation, we need to see what are the kind of general purpose registers that are available in a microprocessor. So, let us look at traditionally the 8085 microprocessor implicitly needed to have one of the registers hard coded and fixed as one of the operands to the ALU, and this happened to be the AX register or the accumulator register. So, A stands for accumulator here, and if you look at the size of this register in the 8086 microprocessor, it is 16 bits in length. So, you have AL which is the lower 8 bits, AH which is the higher 8 bits, and this is AX, the combined register, which is 16 bits in length. So, this is 16, each of this happens to be 8, and just like the instruction pointer where we had an extended instruction pointer for 32 bits, the higher 16 bits is referred to as the EAX. So, the 32 bits is EAX, right. So, here I have E and AX. Apart from this, you can also access 8 bits of AL or AH. So, note that you cannot access the higher order 16 bits of EAX directly as a register. Similarly, I have the other registers which are basically my registers BH, BL, right, and the extended value here again, right. So, this is E, BX, BL and BH, and similarly for CH, CL and my E, and of course, I have one more register called the DX register, DL and my extended value E. So, I have DX, CX, CL, this is also H, CH, DX, DL and DH, and my extended 32 bit registers as well. So, you will find that typically for any of the addition, subtraction, you can use a combination of any of these two registers. You can also use these registers as pointers to something in the memory, which we will come to a little later when we do the move instructions and the ALU instructions in some detail, right. So, apart from this, we also need something known as a stack. A stack is a last in first out kind of memory, and in order to keep track of the top of stack, we need a specific register, and that is known as the stack pointer. SP, and the extended value 32-bit version is ESP. Unfortunately, it is not sufficient if you are able to do just the last in first out kind of operation with the stack. We also need to be able to do some amount of random access, and therefore we have another register which is known as the base pointer, BP and EBP. EBP. Right. So, these are my stack registers. It also it turns out that we are able to do some sort of complicated array manipulation or string manipulation at a hardware level, and for that we have two other registers which are known as the source index and destination index, SI and DI. So, SI and DI, this by the way is the stack pointer and this is the base pointer. Similarly, this is the source index and destination index. Like every other register, I have a 32-bit version of this as well in the modern microprocessors, EDI. So, we will look at some detailed examples of how all of these registers can be used for specific instructions and how they can be exploited to speed up certain functions in C as well later in the course. So, till now we have been referring to we have certain address pointers in memory. For example, the instruction pointer in accessing the code, we have the stack pointer accessing the stack and so on. So, the question is, how do we partition the memory into different segments? For example, I have a large memory . This is my what I want to ensure is the segment where the code is stored is different from where my data is stored, where my stack data is stored and so on. And this is enabled by another set of registers which are known as the segment registers. So, we will talk about So, I have my segment registers which are simply going to demarcate what the different kinds of memories are in a microprocessor. This, for example, is my code. This could be my data. This could be my stack. And this could be my extra segment. So, now the question is, how do I decide that location X to location Y or location A to location B is meant for code, location B plus 1 to C is meant for data and so on. So, code memory, that is achieved by having one pointer to the starting of my code segment. as my CS register. Similarly, pointer to my data segment is my DS register, pointer to my stack segment is SS register, pointer to my extra segment is ES register, and of course the 32-bit extensions are just EDS, ESS and EES and so on. So, if I now have a particular instruction pointer EIP available now, right, let us say that there is some address, it has 0x0010. What is the complete address of this particular location, or where is this location stored in the external memory is the question. So, the way that complete address is constructed is using a combination of the segment register and my instruction pointer register. So, the complete is my ECS code segment register and EIP. This is my complete address. Similarly, if I now am dealing with my stack segment, then the complete address would be ESS stack segment register colon ESP, or ESS colon EBP. So, by default the stack pointer and the base pointer are associated with the stack segment. The instruction pointer EIP is associated with the code segment register. The data registers A, B, C, D are associated with the data segment. The EDI and ESI are associated with the data segment and extra segment respectively. So, with that which is a combination of general purpose registers and some segment registers, we are able to address the entire memory to access code and data. The last register that is needed in order to complete this execution process and is almost mandatory in order to do branching and looping is known as the flag register. So, the flag register is just an indication of a result in because of an ALU operation, arithmetic or logical operation in the microprocessor. For example, if I subtract two registers and it happens to go down to 0, then the 0 flag will be set. If I subtract two numbers and the result is negative, then you have a particular sign bit that is set. So, you can check the value of these bits in the flag register and make certain decisions in order to branch and loop. So, in summary, we have now discussed a bunch of registers that make up a microprocessor in order for the microprocessor to execute this fetch, decode, execute in a loop again and again.